For years, the global technology industry operated on a simple assumption. If we wanted to manufacture the world's most advanced chips, there was one machine you absolutely had to have. One machine built by one company in one country. Without it, the experts said, there was a hard limit to how far you could go. No matter how much money you spent, no matter how many engineers you hired, no matter how determined you were, that machine was called EUV lithography, and China wasn't allowed to buy it. The logic seemed airtight. No EUV meant no cutting-edge chips. No cutting-edge chips meant no path to the most advanced AI, smartphones, supercomputers, or future technologies. The restriction wasn't designed to slow China down. It was designed to stop China at a specific point and keep it there, but something unexpected happened. Instead of stopping, China found another route, a route that many experts believed was too expensive, too complicated, and too impractical to ever work at scale. And yet today, a Chinese-made 5-nanometer class chip exists, not in a laboratory, not as a prototype, inside real products that people can actually buy. The most surprising part isn't that China built the chip, it's that China built it without the very machine the world said was required. By the end of this video, you'll understand how they pulled it off, why so many analysts thought it was impossible, what it cost them, and why this breakthrough may have exposed a weakness in the entire strategy designed to contain them. To understand why this story has attracted so much attention, you first need to understand the machine everyone was talking about in the first place, because this isn't just another manufacturing tool. It may be one of the most sophisticated machines humanity has ever built. The machine is called an EUV lithography system. EUV stands for extreme ultraviolet, and while the name sounds complicated, the basic idea is surprisingly simple. Modern chip manufacturing is essentially a printing process. Engineers take a silicon wafer and print incredibly tiny patterns onto its surface. Those patterns eventually become billions of transistors. The smaller and more precise the patterns, the more transistors you can fit onto a chip, and generally speaking, more transistors mean more computing power. For decades, the semiconductor industry advanced by making those patterns smaller and smaller. The challenge is that printing smaller features requires shorter wavelengths of light. And eventually the industry reached a point where traditional tools simply couldn't keep up. That's where EUV entered the picture. EUV machines generate an extremely short wavelength of light capable of creating the tiny features required for advanced chips. Sounds simple, it isn't too. The engineering involved is almost absurd. Each EUV machine contains hundreds of thousands of components. Each system costs well over $200 million. Some of the mirrors inside are so precise that if they were expanded to the size of Germany, the tallest imperfection would be smaller than a millimeter. The machines fire lasers at microscopic droplets of molten tens of thousands of times every second to create the required light source. Even describing the process sounds like science fiction. And for years, there was only one company capable of building these machines, the Dutch firm ASML. That fact became one of the most important realities in modern technology, because if only one company can build a machine required to manufacture the world's most advanced chips, access to that machine becomes a strategic advantage. Eventually, it became a geopolitical one. When restrictions prevented China from purchasing EUV systems, the assumption throughout much of the industry was straightforward. Without EUV, China would eventually hit a ceiling. Maybe not immediately, maybe not next year, but eventually the logic made sense. After all, every major semiconductor leader relied on EUV to push toward the most advanced process nodes. TSMC used it, Samsung used it, Intel used it. The entire leading edge of the industry used it. So if China couldn't access the machine, how could China possibly keep up? And that question became one of the defining assumptions of the semiconductor race. And assumptions are powerful things. The longer they're repeated, the more permanent they begin to feel. Analysts repeated them. Investors repeated them, governments repeated them, technology publications repeated them. Over time, many people stopped treating the idea as an opinion. It became accepted fact. Then something interesting happened. Chinese engineers started asking a different question. Not how do we get EUV, but how far can we go without it? At first glance, that might seem like a small distinction. It's actually enormous, because once you stop focusing on obtaining the ideal solution, you start looking for alternative solutions. And alternative solutions often emerge from places nobody expects. The machine China still had access to was called DUV lithography, deep ultraviolet, an older generation of technology, less advanced, less precise, and according to conventional wisdom, incapable of producing truly cutting-edge chips. And the common analogy is drawing. Imagine trying to create an incredibly detailed sketch. EUV is like using an ultrafine technical pen. DUV is like using a much thicker marker. If you want the smallest possible details, you naturally want the fine pen. The marker seems inadequate, but what if you couldn't access the fine pen? Would you simply stop drawing, or would you find another technique? That's essentially the challenge Chinese engineers faced, and their answer was something called multi-patterning. And the concept sounds technical, but the logic is surprisingly intuitive. Instead of creating the final pattern in one pass, you create it in multiple passes. Carefully, repeatedly, building complexity layer by layer. Imagine painting a detailed mural, and one artist completes it with a single sophisticated tool. Another artist lacks that tool, so they use multiple masks, multiple passes, multiple stages. The second approach is slower, more complicated, far more demanding, but if executed perfectly, the final result can look remarkably similar. And that's the strategy SMIC pursued, not because it was easy, because it was available, and availability often matters more than elegance. Reports suggest the company pushed advanced multi-patterning techniques to levels many experts considered commercially unrealistic. The process required extraordinary precision. Each step had to align almost perfectly with the previous step. Tiny errors could ruin the final result. Tiny defects could destroy the chip. Tiny variations could reduce yields. This is where the story becomes particularly fascinating, because technological breakthroughs are often portrayed as moments of inspiration. A genius has an idea, a company develops a product, the world changes. Reality is usually much messier. Most breakthroughs are actually stories of persistence, stories of engineers solving thousands of small problems, stories of teams spending years reducing error rates by fractions of a percent, stories of people refusing to accept limitations everyone else considers permanent. And that's exactly what appears to have happened here. SMIC didn't magically bypass physics, and they didn't discover a secret technology hidden from the rest of the world. Instead, they pushed existing technology much further than many observers believed practical. And eventually, the results started appearing. When analysts examined Huawei's newer processors, they found evidence of manufacturing techniques that seemed impossible under the old assumptions. Not impossible according to physics, impossible according to industry expectations. There's an important distinction there, because expectations and physical reality are not the same thing. History repeatedly shows that industries often confuse the two. Something becomes expensive, difficult, inefficient, or unattractive. And then people start calling it impossible. Years later, someone proves otherwise. And the semiconductor industry is filled with examples. Challenges once considered insurmountable eventually became routine. Manufacturing limits disappeared. Design barriers fell. New techniques emerged. What matters isn't whether something is difficult. What matters is whether someone is willing to endure the difficulty long enough. And China had a powerful incentive to try. If you're finding this story as fascinating as I do, take a moment to leave a like. Not because it helps me in some algorithmic race, but because it tells me there are people who enjoy understanding the deeper engineering stories behind global technology. Those are the conversations I genuinely enjoy most. And they're the reason videos like this exist. Now, before anyone jumps to conclusions, it's important to be honest about what this achievement does and doesn't mean. It does not mean China has suddenly surpassed every semiconductor leader. It does not mean SMIC has matched TSMC's manufacturing efficiency. It does not mean restrictions became irrelevant overnight. In fact, many challenges remain, and some of them are enormous. Because while finding a workaround is impressive, turning that workaround into a scalable, cost-effective manufacturing process is an entirely different challenge. And that's where the next chapter of this story becomes even more interesting, because proving something is possible is only the beginning. The real battle starts when you try to make it practical. Here's where the story becomes much bigger than a single chip. Because when most people hear that China built a 5-nanometer class processor without EUV machines, they immediately focus on the engineering achievement itself. And to be fair, it is an extraordinary engineering achievement. But the larger lesson may have nothing to do with nanometers. It may have everything to do with incentives. Technology industries tend to move in the direction of least resistance. And if the best tool is available, everyone uses it. If the fastest path exists, companies take it. If the most efficient solution can be purchased, nobody spends years developing alternatives. That's simply how markets work. Restrictions changed that equation. The moment access to EUV disappeared, Chinese companies were forced into a completely different mindset. Instead of asking, how do we buy the best technology, they start asking, how do we recreate the capability ourselves? Those are fundamentally different questions. One optimizes for efficiency, the other optimizes for resilience, and resilience often produces unexpected results. Think about aviation. If an airline can buy engines from the world's best supplier, it probably will. But if access disappears, the airline eventually starts investing in alternative suppliers, alternative designs, and alternative capabilities. Those alternatives may initially be worse, more expensive, less efficient, but over time they improve, and eventually the gap begins to shrink. That's the dynamic many analysts believe is now unfolding inside China's semiconductor industry. Because the most important thing restrictions can do is slow progress. The most dangerous thing they can do is motivate independence. And those are not always the same outcome. The reality is that China poured enormous resources into domestic semiconductor development after restrictions intensified. Billions of dollars flowed into manufacturing, equipment, materials, research, universities, talent developments, supply chains. Entire ecosystems began expanding simultaneously, not because it was easy, because it became necessary. Necessity is one of the most powerful forces in technological development. History proves this repeatedly. Countries facing shortages innovate. Industries facing constraints adapt. Companies facing barriers experiment. Not every effort succeeds. Many fail, but enough succeed to gradually change the landscape. That's what makes this semiconductor story so important. And the question is no longer whether China can produce advanced chips. And that question has largely been answered. The more interesting question is how quickly China's broader ecosystem can continue improving from here. Because a chip is never just a chip. Behind every processor sits an enormous network. Materials suppliers, chemical manufacturers, equipment makers, software developers, packaging companies, research institutes, universities, design firms, testing facilities, thousands of interconnected organizations. The semiconductor industry isn't really one industry. It's dozens of industries operating together, and historically, that's where the biggest challenge existed. Building one impressive chip is difficult. Building an entire ecosystem capable of repeatedly producing them is vastly harder. That's the challenge China is still working through, and it's why this story remains unfinished. Now, one thing I think often gets lost in these discussions is perspective. Technology reporting sometimes treats competition like a sporting event. One side wins, the other side loses. One breakthrough changes everything. The game is over. That reality almost never works that way. Technology leadership tends to evolve gradually. Even major breakthroughs rarely transform industries overnight. TSMC didn't become dominant in a year. ASML didn't become indispensable in a year. NVIDIA didn't build its AI position in a year. These advantages accumulated over decades. And the same principle applies here. Even if China continues advancing rapidly, catching up across every dimension of semiconductor manufacturing remains an enormous undertaking. There are still gaps, there are still bottlenecks, there are still technologies that remain extraordinarily difficult to replicate. But what's changed is perception. A few years ago, many observers believed certain barriers were absolute. Today, they look much less absolute. And perception matters because perception influences investment. Investment influences innovation. Innovation influences outcomes. That's why so many governments, companies, and analysts are watching this story closely. Not because a single chip changed the balance of power overnight, because it challenged assumptions people once treated as unshakable, and when assumptions start breaking, strategies often change. I want to pause for a second here because this is one of my favorite parts of making videos like these. If you've watched this far, you're probably someone who enjoys understanding the deeper forces shaping technology rather than just following headlines. And honestly, that's rare. If you're getting value from these conversations, consider subscribing, not because I'm chasing subscribers, but because these topics are moving incredibly fast, and it's genuinely fascinating to follow them together over time. Some of the best insights I encounter actually come from viewers in the comments who see angles I completely missed. And that's something I appreciate more than you probably realize. And now let's talk about the bigger strategic question. What happens if alternative paths continue emerging? Because this is where the implications extend far beyond China. The semiconductor industry has spent decades optimizing around specific assumptions. Certain machines were considered essential. Certain suppliers were considered irreplaceable. Certain technologies were considered mandatory, but history shows that industries become vulnerable when everyone depends on the same assumptions. Sometimes innovation comes from improving the existing path. Other times it comes from finding a completely different one. And the fascinating thing about China's approach is that it demonstrates how powerful alternative paths can become when enough resources are dedicated to them. Not necessarily better paths, not immediately, but viable paths, and viability changes everything. The existence of an alternative often matters almost as much as the quality of the alternative itself. Because once alternatives exist, competition increases, options increase, leverage increases, the entire ecosystem becomes more dynamic. That's true in technology, it's true in economics, it's true almost everywhere, which brings us back to the original question. Did China build a 5 nanometer class